Since the beginning of our existence, the sun has played a vital role in our daily lives. It has provided us with warmth and light. It warms our seas, it generates our weather patterns, and it gives energy to grow for the plants we eat. Our very existence is contingent on the sun's heat and light. But how much do we really know about the sun? Although we're aware of its basic significance on our planet, there's a lot more to it that needs to be explored. We may see the sun as a bright yellow orb in the sky, but there are many more components that create it. Like the Earth, the sun is composed of various layers, each layer more dense and compact as you go deeper. The only difference is, each layer becomes cooler the deeper they are. The sun's core is made up of three inner layers: the core, the radiative core, and the convection zone.
A star is nothing but a sphere of glowing gas. It forms out of a compressed cloud of gas and releases energy steadily throughout its life because of a continual chain of nuclear reactions that take place at its core.
The energy in the form of heat and light are produced in these layers. The outermost layers of the sun are made up of the chromosphere, the transition region, and the corona. These layers have significantly higher temperatures than the inner core of the sun. As a result of the compressed hydrogen gases, nuclear fusion occurs, creating a number of occurrences that the sun emits throughout the solar system. But how are we able to create these measurements and collect enough data to at least attempt to predict the sun's emissions? The Solar and Heliospheric Observatory, otherwise known as SOHO, has been monitoring the sun and its activity for almost 20 years. It is an international collaboration between NASA and ESA. It launched in December 2nd, 1995. It was originally intended to study the sun's core.
First burn of the Centaur upper stage placed the SOHO vehicle in a circular parking orbit about the Earth. The second Centaur engine firing successfully sent SOHO into a transfer trajectory towards its final orbit. Its mission complete, the Centaur stage separated. In this time frame, the initial sun acquisition and the solar array deployment had been achieved, and the SOHO flight operations team based at NASA's Goddard Flight Research Center had used the uplink channel to send commands to the spacecraft for the first time. After a 4-month journey, the spacecraft reached its vantage point in orbit 1.5 million kilometers nearer to the Sun than the Earth's own orbit. There, at L1, or Lagrange point number 1, the gravitational pull of the Sun is balanced by the pull of the Earth, and the centrifugal force acting on the spacecraft orbiting in step with the Earth, SOHO can therefore remain hovering around a relative position, in a halo orbit while it accompanies the Earth in its annual march around the Sun.
SOHO was originally intended to study the sun's core and its outer corona and solar wind. Most of its data is collected from seismic waves produced from the turbulence in the sun's outer shell, such as the first images of a star's convection zone, the discovery of coronal waves, and the discovery of solar tornadoes. It is designed as a 3-axis stabilized spacecraft that always faces the sun. It contains 2 modules, the payload module that contains 12 of its data collecting instruments, and the service module that provides basic essentials such as thrusters, communications, and power. Others are used to track motion on the sun's surface, as well as its corona. SOHO is operated from NASA's Goddard Space Flight Center in Washington, where an integrated team of engineers from NASA work under the supervision of ESA.
We may not be able to see it, but the sun emits more cosmic rays than warmth and light. There are occurrences that happen on the outer layer of the sun. A notable example is the emitted coronal mass ejections, or CMEs. CMEs often take about 5 days to reach the Earth after emission. They are considered to be shock absorptions from the sun's corona that are ejected by a prominence or a solar flare. Contrary to popular belief, CMEs are not part of the solar wind, but they do interact with solar wind along with interplanetary magnetic fields. CMEs occur in inversely proportional ranges in the sun's 11-year cycle. They can sweep throughout the majority of the solar system, being able to reach up to the distance of Uranus. While their origins are still unclear, a widely spread theory states that CMEs are a result of the realignment in the sun's magnetic fields. Solar occurrences hold a substantial effect on the Earth and our daily lives. Humans at high altitudes are vulnerable to exposure to the sun's rays. Astronauts and commercial air passengers are prone to exposure to more concentrated ultraviolet radiation from the sun. Our modern technological systems, including communications, transportation, and power systems, are susceptible to damage from solar storms. Another result from a solar storm impact on the magnetosphere is that it can induce electric currents at ground level that can destroy electrical power grids, interrupt phone lines, and increase the corrosion in pipelines. By studying the sun and its weather occurrences, we can be able to predict the forecast, any potential threats it can bring from CMEs and solar storms. Any forecasted solar weather can help prevent the destruction of technology and power sources that the world heavily relies on.
Although the sun may have given us life, the potential damage that can be inflicted stands as a stark reminder that life on Earth continues to exist only under the permission of the sun. However, the ability to forecast solar weather can help provide a substantial amount of help controlling the damage that can be done to our planet. While we may be getting better at predicting the weather patterns of the sun, in terms of technology and data collection, we still have a long way to go. After all, the forecasting of the next solar storm will be vital to our very existence.